Hello again, my dear students, and welcome to our new chapter dealing with metal oxide semiconductor field effect transistor, or the MOSFETs. This will be chapter number 4. In chapter number 1, we have a quick revision about the course content or the previous course content related to the material. Then in chapter number 2, we go to the p-n junction. Chapter number 3, we have dealt with what's called the metal oxide junctions, and now we are going to the metal oxide semiconductor field effect transistor, or what is abbreviated by MOSFET. Believe me or not, this is a core chapter in this module. Maybe this would be reflected even in the final exam, as you believe, and we also have discussed this previously, that MOSFETs are considered as the most important building block for all analog/digital electronic circuits. That's why we will give a special interest and a special depth as well for our MOSFET study. Now, please let me share my presentation slides and start with you the journey for chapter number 4. Okay, as I mentioned, our chapter is titled by metal oxide semiconductor field effect transistor, or what's called MOSFET. Now, what we should do with this MOSFET? As we did for the p-n junction, as well as for the metal semiconductor device, junctions, whenever we are studying a semiconductor device, our interest will start with understanding the concept of carrier transport through demonstrating the energy band diagram. And then we transfer to a next step, which the IV characteristic curve, in order to study the different region of operation for our device. We did this for our p-n junction diode, and we will going to repeat the same procedure while dealing with MOSFETs. So now let's start this process. First, let's start describing the schematic for a MOSFET. This is in the extreme left side. You can find a 3D schematic for the MOSFET, while in the 2D, in the right-hand side, you can find the 2D schematic. MOSFET consists of a substrate. The substrate is the bottom layer of the material where you are going to fabricate your device on. So our device consists of, so we have the substrate. Above this substrate, we start to construct or to fabricate our device. Our device consists mainly of two important points, or two important regions. What's called the source well and the drain well. As you can see, there is always an alternating between the substrate type and the source and drain type. For example, herein we have a p-type substrate, and then we have an n-type source and drain. We can have the other alternative to have an n-type substrate and a p-type source and drain. Regarding the contact of our device is a 4-terminal contact. As you can see, we have a contact through the source, another contact through the drain, a third contact to the body or the substrate, and now a fourth contact, which is directed to the region between the source and drain, which we will call it later on the channel region. Above this channel region, we have a dielectrical, an insulating material, an oxide material. As you can see, this white layer, and then you have what's called the gate contact. So we have the source, the gate, the drain, and the body. These are our 4-terminal device. Now, as I mentioned, usually our first step is to start plotting or sketching the energy band diagram of our device. And now, as you can see, this is not as simple as a p-n junction where you have only 2 terminals. You have a p side and n side. Here you have a 4-terminal and a different region. So we can have different types of energy band diagram. Let's start with a cross-sectional energy band diagram. What I'm going to do now, my dear students, is that I'm going to plot an energy band diagram. Let me use the annotation to describe it. So I'm going to plot an energy band diagram in this cross-sectional. So if you use this cross-section, then you will find that you have an N-type region, then you have a P-type region, and then you have an N-type region. So what we are going to plot now, my dear students, is something considered as an NPN junction, as you can see. This is the first type of energy band diagram that we are going to use in order to describe the carrier transport strategy inside the MOSFET. So now let me turn to my symbol whiteboard and start describing this PNP junction. As usual, whenever we start to plot an energy band diagram, your first step is to have a thermodynamic equilibrium condition. And these thermodynamic equilibrium conditions occur whenever the Fermi level is an horizontal line. So we start by plotting the Fermi level to represent a thermodynamic equilibrium condition. After that, we start to plot or sketch our conduction and valency band with respect to this Fermi level. So as I'm describing in the presentation slides, our current junction considers or is of three regions. We have a source, which is an N-type. We have a channel, which is a P-type. And we have a drain, which is an N-type. So what we are going to plot now is an NBN junction. So for an N side, the EC is more close to EV with respect to EC is more close to EF with respect to EV. Same is here. While in the P side, we have something like that. So you can now connect this together. That's perfect. So this is the thermodynamic equilibrium for the NBN junction found in the cross-sectional cut through the source, the drain, and the channel in between. Now, do we have a continuous carrier flow due to this NBN junction? Now, what do you mean by carrier flow? That, for example, here in the source is an N-type. As far as the source is an N-type, so we have to expect that the majority of carriers is electrons. Does these electrons capable to move to the drain? The answer simply is no, because these carriers will face a barrier here and will not be able to pass this barrier as far as this barrier exists. Similarly here, you have also a majority of electrons here in the drain side, but these electrons will not be able to move to the other side due to the barrier. Even the holes here, the holes in the B side in between region are restricted in this wall and are not able to move either to the left side or to the right side. Accordingly, under this condition, no continuous electrical current will be conducted. And in order to have a flow of current, then you have to get rid out of this barrier, because this barrier is the obstacle which prevent electrons from passing from the source to the drain. So now let me return back to the presentation slides. So this is the energy band diagram, similarly to the one I just plotted on the whiteboard. So you have here electrons, you have here electrons, but these electrons are not able to move, and these electrons are not able to move. Even these holes are not able to move. So this is the thermodynamic equilibrium condition. Again, it's a thermodynamic equilibrium because you have a flat horizontal Fermi level. Okay, so what is next? Now we are working toward making or pushing this electron to move from the source to the drain. So we need to get rid of out of this barrier. In order to get rid out of these barriers, it simply means that to push this P region downward so that you can get this barrier out. how we should or how we can make this push. Let's see. The first step in order to make your MOSFET to conduct is to have a voltage on the gate. This voltage should act to push the energy band diagram downward. How we can make something like that? Let's turn back one slide backward. The problem here that this region is a p-type. What if we act to have this region to be converted or inverted from a p-type region to an n-type region? In this case, the Fermi level will go upward, or this band will go downward, and no longer barrier exists. So what we are going to do is to invert this region, this slide under the oxide layer, to be an n-type. How we can do so? So what if we apply a positive voltage to the gate? As you quite sure know, positive voltage shall attract electrons and repel holes. But you will tell me that please take care. This blue area, which represents the substrate, is a p-type material. So this area includes a huge amount of holes. That's true. But it still contains a minority amount of electrons. So once you add this positive charge over the gate, an electrical field will be propagated through the oxide. And the first step that you are going to repel holes from this layer. Then you are going to attract electron. The higher the gate voltage is, the higher your attraction capability to attract the electron. Till you build what we call a bridge, or officially what we call a channel, linking the source side with the P side, with the drain side. This channel should be an n-type channel due to the attracted electrons by this positive charge. The voltage at which this channel is created, we call it the threshold voltage. I'm quite sure that you hear this term before in your electronic courses, what is called the VT or the VTH or the V threshold. So by definition, the threshold voltage is the voltage needed on the gate in order to make or to invert this channel region from being a p-type substrate to being an n-type, linking the source to the drain. And in this case, you can now have a carrier flow between the source and the drain. So I will return back now to my slides again, or sorry, to not my white paper, and let's start to discuss what if we apply the voltage here on the gate so that the gate becomes, or the channel become, an n-type and not a p-type. So now the channel is an n-type, so this Fermi level should move upward, or in other words, this EC and EV should go downward. So what will happen is as follows, my dear students. And this is our Fermi levels. No longer horizontal Fermi level. This barrier disappear, and now you have a drift. So you have electrons here, and you have electrons here, and these electrons can move to go to the other side without any problem. But the question is, why this electron should move? If you return back to the slides, you will find that I put the drain to the ground and the source to the ground. So these two potentials are equal, are on the same level. So theoretically speaking, there is no reason for these electrons to move to the right, or for these electrons to move to the left. Accordingly, this is a very important point, my dear students. Putting voltage on the gate equals to or greater than V threshold makes this barrier disappear. However, It's not enough to make current move. You should attract electrons somehow to move either in this direction or in this direction. So the gate voltage alone is not enough for a current to move inside the MOSFET. So let's see what should we do as a next step. Okay, so the first step is that we put this gate voltage as a positive voltage to attract electrons on the channel and convert it into or convert the substrate to be a channel, which is the threshold voltage. Now, what is the second step? The second step, my dear students, is to have this positive voltage. Now, once you start to put a voltage on the drain, that means that these electrons in the source are now attracted to move to the drain. Now you can see my pointer on the top right of your screen, in my screen, so that these electrons now attracted to this side, because simply you have a positive charge to the drain. So electrons are now attracted to go to the positive charge, to the positive side, or to the positive charge. Now, this is the reason to have a current flow. Accordingly, in order to have a current flow in a MOSFET, you should satisfy two conditions. The first is to build a channel to make the bridge between the source and the drain. And this happens whenever you put a gate voltage equals to or greater than the threshold voltage. The second step is to create a motivation for the electron to move by inserting a positive voltage to the drain. So electrons in the source starts to move to the positive charge in the drain. Herein, you can clarify two important points. The first is why we call source is a source and why we call drain a drain. The source is the source because this is the source of electron. This is your stuck. And the drain, this is the termination of your electron journey. So electrons starts to move from the source toward the left-hand side, also to the right-hand side, towards the drain, which is the termination till it reaches the contact. Another point we already have discussed in the metal semiconductor chapter 3, which is what's called the unipolar and the bipolar devices. If you remember, whenever we make a comparison between the Shockley diodes and the PN junctions, and I told you that we will call this comparison again whenever we study the MOSFETs and the BGT. As you can see here, current is conducted only due to electrons. That's why we call the MOSFETs as a unipolar devices. We have an N-channel MOSFET where current is only due to electron. And we have also a P-channel MOSFET where current is only due to holes. However, in your next chapter dealing with BGT or bipolar junction transistor, you will know that in the BGT, it's a bipolar. Its name is bipolar. So by default, it's a bipolar device. I mean, the current is due to both electrons and holes. Okay. Now, what happens if we start to increase more and more the voltage into applied to the drain? What will happen if we increase this voltage more and more? What the effect of this increasing on the schematic, on the energy band diagram, on the performance of the MOSFETs? So let's start to address this point. Okay. As a very quick flashback, we start with this schematic. We have source, a drain, then we have this oxide layer, and then we have a metal contact where we have the gate voltage. Once you apply a voltage positive here, electron starts to be attracted from the substrate and constructing the channel or this bridge between the source and the drain. So this is the inverted layer constructed due to the positive charge applied to the gate. Now, what we did is that we are going to have a higher and higher voltage here to the drain. And then we are discussing what's the effect of this. Okay, so in order to make you understand this concept, I usually use a very preliminary example. I believe all of us did whenever we are kids, is the example of a magnet and a piece of metal. So, for example, let's examine that you have a permanent magnet, a piece of a permanent magnet. And you have any type of metal that is attracted, a very small piece of metal that can be attracted by the magnet. Okay, so if I told you that I put this piece one time here, one time there, and one time here. So this is position number 1, position number 2, and position number 3. Which of these positions has the maximum probability to be attracted? Obviously, it will be position number 1. Because position number 1 is the most close to the permanent magnet. So the probability of attraction is maximum at 1 and is minimum at 3, because 3 is far, so there is still debate. Maybe it's attracted or not. Accordingly, if I told you that I have 3 electrons here, similarly 1, 2, and 3, which of these 3 electrons have the highest probability to be attracted? Again, this is electron number 1, because it's the most close one to the positive charge, which is the analogy of the permanent magnet. And as far as you go towards the source, the probability of attraction reduced. So in this region, typically, I mean the boundary between the channel and the drain, we can say that at this region, typically, the probability of attraction is very, very, very high. And logically speaking, this probability of attraction increase as far as you're increasing the voltage on the drain, because you are increasing the attraction force. The higher the voltage, the higher the attraction force. So by increasing the VDD, I will replot the channel in this manner. This is a drain, this is a source, and this is a gate. You have here a positive voltage which is equals to or greater than V threshold, and you have also here VDD which is somehow high. Now, while I start to plot the channel, I will plot it something like that. Okay, so why this ramp? This is typically due to probability. The channel is created because of electrons, and as the probability to attract electron is very high here, then you have lower electrons here. Once you go toward the channel, the probability to find an electrons increase, so you have higher electrons here. So you have this ramp structure, indicating that here the probability of electrons is greater than here. And this ramp starts to be with higher slope as far as you increase the drain voltage, because as far as you increase the drain voltage, low electrons appears in this point because the attraction force is very high. Let's do it using the presentation slides. Okay, perfect. So what will happen is as follows. This is the reduced channel or the ramped channel due to having a higher drain voltage applied to the drain. As much as you increase the drain voltage, this point starts to reduce more and more, because it indicates that this is a lower probability, that's right, to find electron, because once the electron reaches this point, it will be directly attracted to the drain till we reach what's called the pinch of point. The pinch-off point is the voltage applied to the drain at which this channel reach a width 0 at the channel drain interface. And typically or mathematically, this is equals to VGS minus V threshold. So whenever the VDS or the voltage applied to the drain equals to VGS minus V threshold, we reach this pinch-off point. The pinch-off point, or the corresponding to what we call the VD sat, is the point at which the channel vanish at the channel drain interface. So once you start to increase the voltage greater than VDS sat, or the pinch-off voltage, your channel will start to disappear and go toward the source, as you can see. So now the pinch-off point is here when VDS equal VDS sat. Whenever you increase this VDS greater than VDS sat, the pinch point starts to go toward left, towards the source. Now, what is the difference in the current flow? Let's go to this slide to describe. First, this is the first case, whenever you don't have a gate voltage. So in this case, VGS is smaller than V threshold, so we don't have a channel. Accordingly, there is no current. And we call this the cutoff region. So the cutoff region is the region at which the voltage applied to the gate is smaller than the V threshold. So you don't have a channel linking the source to the drain, and accordingly, you don't have current. Once you put a voltage equals to or greater than the V gate, then your channel will be created. And as far as you have a voltage applied to the drain, then electrons will start to move from the N side to the P side, conducting electrical current. So this is the way we have current. You can easily understand that the higher the drain current, more and more electron will be attracted, and accordingly, more and more current. So the higher the drain voltage, the higher the current. So in this stage, the current is directly proportional to the drain voltage. You increase the drain voltage, so more attraction force, so more electrons comes from the source to the drain, so more current. Okay, but at a certain point, which is the pinch-off point, this VD well tends to have a channel with a 0 width at this barrier point. So once you narrow down the channel, that means that you have a higher resistance here. And this resistance increased by this. So let's go to typically to this example. So here we have, this is the source, and this is the drain, and this is the channel. This is the normal way of the channel. Whenever you increase the voltage of the drain, the channel will start to narrow down till you reach the pinch-off point. Then the channel will have something like that. If you increase your voltage greater than the building potential, the VDSAT, here VDS equal VGS minus V threshold. If you increase more than that, then you will have something like that. Now you have this pinch-off. Let's make it in a better paper. So now what's happening is that this pinch-off point starts to move. So now is this point VDS is greater than VDS sat. So what or how this will affect the current? In the normal stage, Electrons move freely from the source to the drain as far as there is a positive voltage applied to the drain. So electrons are moving safely. There is a bridge linking to the source to the drain. However, as you can see here, the electrons here will start to move to the bridge, but at a certain point, the electron will find that the bridge is no longer continuing, and this region is not an n-type region. And by the way, it's not also a p-type. Why? It's not an n-type because there is a high attraction force here. So whenever you have an electron here, this electron is directly attracted to the drain. So no electrons stays here. And it's not a p-type because please don't forget that you have a positive charge applied to the gate. So this positive charge will repel holes from this region. So this region becomes a depleted region. Accordingly, we have electron here, and this is a channel, but now this is a depleted region. If you remember, the depleted region is a region with a very high resistance. It's some sort of insulating material. So once the electron reaches this point, it will only pass the barrier or the depletion region because of this high, very high attraction force due to the drain. It's something like a tunneling effect. The electron tunnel this depletion region in a very high velocity. But you can easily understand that the electron motion here is more easy than the electron motion here. Here you have a constant flat resistance. Electrons move freely from the source to the drain. The bridge is completed. The bridge connected the source to the drain. However, here you have an uncompleted bridge. The bridge consumes only 50% maybe of the journey, and the other 50% will have a very high resistance. That's why when we start to reflect this on the IV curve of a MOSFET, you will find something like that. This is the typical or the ideal IV curve for a MOSFET. First, when VGS is smaller than V threshold, this blue line on the x-axis, you don't have a current. And this reflects what's called the cutoff region. Current starts to conduct whenever VGS is greater than V threshold. Now, we have two regions with respect to the drain voltage. The first region is when the drain voltage is small. I mean, the drain voltage is smaller than the VDS SAT or VGS minus V threshold. In this case, which reflects this case, by the way, the top right case, current is directly proportional to the voltage, as you can see here, which we call the triad region. So in this region, current is directly proportional to the voltage. The higher the drain voltage, the higher the drain current. However, once a pinch-off occurs, this current starts to saturate and see this saturation resistance, as you can see, which reflects an infinity resistance because, as you know, the slope, the 1 over the slope of this curve represents the resistance. This is I and this is V, so the slope is I over V and the resistance is V over I. So whenever you have an horizontal line, that means that you have an infinite resistance, which is the resistance due to this depletion region occurs whenever VDS is greater than VDS SAT, or due to the pinch-off point shifted towards the source. So this is how the IV curve looks like. However, in a realistic case, nothing is infinity. We have a very high resistance in the saturation region, but it's not typically infinity. So whenever we turn from an ideal IV curve to a realistic IV curve, we should see something like that. As you can see, Now this line is no longer in horizontal line. It starts to have some slope, and this slope, or 1 over this slope, represents the output resistance of this iteration of the MOSFET. Of course, it's very, very high resistance, but it's not infinity. That's why we have this slope. So this is what we call the realistic IV curve for a MOSFET. Now, as a final stage in this lecture, or in this part of the lecture to be accurate, this, as I told you in the beginning, we have two types of a MOSFET. The first type, what we call the N-channel MOSFET, where we have a P substrate, an N plus source and drain, a metal, a gate, a gate, a source and drain. We put a positive charge on the voltage on the gate in order to attract the electron here and to create a channel between the source and the drain. On the other hand, you can have what we can call a P-channel MOSFET. Herein, your substrate is an N type, your source of drain is P type, so you are requested to put a negative voltage to the gate to acquire or to attract holes in the channel and create your P channel. And you are requested now to put your positive, your negative voltage on the drain so that you can attract holes from the source to the drain. So now source is positive and drain is negative. That's why holes are attracted from the source to the drain. So this is the other type, or what we call the P-channel MOSFET. In your next semester, in your VLSI course, you are going to build all your digital circuits based on these two MOSFETs, the N-channel MOSFET and the P-channel MOSFET. And you are going to combine them together in the same circuit under the technology of the CMOS, or the complementary metal oxide semiconductor technology, which is the most famous technology in the IC, in the digital IC design theory. This is a termination of part number 1 in lecture number 4, dealing with MOSFETs. In the next part, we are going to discuss again the MOSFET, but with another perspective. We are going to consider two main important points about the MOSFET. The first is what we call the metal oxide semiconductor junction, or whenever we have an energy band diagram in this vertical manner rather than the horizontal one we did in this report. And the second is what's called the MOSFET capacitance. The MOSFET capacitance is one of the most important parameter associated to the MOSFET whenever we are studying a MOSFET in a circuit. So thank you very much for your concentration, and see you next part with part number 2, chapter number 4. Thank you, and see you later on.